you can get something like this. This is one of those two possibilities. So now, does that explain the distribution of oil and gas? Well, okay, here's the gas is down here, okay, and so that's a different reservoir. We already determined that. And here's your base of your incise valley in red there. And here you've got oil up dip of the gas, but it's two separate reservoirs. And now you go further up dip and you've got oil plus gas. So one possibility is that this is a separate isolated reservoir right in here. Now you go up to the next well where you've got just oil, 292 barrels of oil, and that's sitting down low on the in that sand body, and you go higher, structurally higher, and you get oil plus gas. So you've got a gas-oil contact somewhere up in here. So that explains, or that's one explanation for the distribution of oil and gas. And you could not just do the stratigraphy, you could not just do the structure, you had to work out both of them to figure it out. And it's usually easiest to do the stratigraphy first, and so you can do your correlations and then add the structural interpretation. Now, the reason I gave you a second possibility, I said that this was a possibility as well, and that relates to the distribution of the oil and gas. Because if we do this now, we've got oil down low here in that sand body, and as we go up dip in the same sand body, we get oil plus gas. So that would put a gas-oil contact somewhere in here, plus your gas-oil contact somewhere in there. So that is why I put this as an additional possibility. But you can't rule that out because you're going from oil structurally low in that sand body to oil plus gas structurally high. And if you wanted to get gas, you presumably if you drilled higher here on the structure, through the top part of the sand body, you'd get a higher higher gas-oil ratio. So that's a real example, and these sand bodies that occur in that basin, the Wattenberg gas field, produces from these types of sand bodies. And remember I said earlier, before lunch, I'm going to go back a ways here now, and I said before lunch that what you see is a big giant gas field here in red, and a lot of small fields in red. Some of them are gas fields in red, some of them are oil fields in green. And this is why. They're just isolated sand bodies, incise valley fill sand bodies that are of different sizes and shapes and so on. Okay, so at any rate, it looks like you all figured that out, so that's good. So I'm going to move on then and show you another example. And up here in this upper right, acting up today. Not doing too well. Let's try this. Oh, I know why. Okay, excuse me. Let me move ahead one slide, then I'll come back to that one. What we're looking at here is in the same general area, the Denver Basin, where the Wattenberg gas field is again. But now we're looking at another field called the Sorrento field. It is an oil field. And it's a good producing field. Now, where a lot of wells have been drilled in that field. In fact, here you see all of the wells. The black dots are oil wells, and then you've got some non-producers that outline the edge of the field. So the first thing you notice when you do an isopac thickness map of this is that you've got this kind of right angle bend here that looks very much like it'd be a meander loop where you'd have a point bar system. So that's your first observation that you can make. Now, the second observation is where we go back and look at the logs, and several of these wells were cored, so we had good core control for our logs. What you see in the log is what looks to be a very simple sand body, an individual sand body, and but when you look at the core is much more complex, in that there's actually 3 different sand bodies, which we called flow units. Remember, I used that term yesterday. Flow unit 3, flow unit 2, and flow unit 1. This is a computed lithology log. Here's a permeability profile. And when you look at that, what you see is the permeability increases from left to right. So you're at 1,000 millidarcies up here to the right. So you get very high permeability in this flow unit 1. Flow unit 2 has high permeability, not quite as high as 1. But then you get into flow unit 3 and the permeability drops dramatically. When you look at the geologist looked at the sedimentary rock types, the sedimentary facies types, found that you had a marine shale down here, and that's what gives you the shaly log response right there. And just a little bit of a marine interval, that's not very important. But then you had a fluvial channel sand, was the main reservoir sand that covered flow unit 1 and 2, and part of flow unit 3 as well. Then stratigraphically above that, you have what's called here reworked sandstone, which in this case, the reworking means it's been reworked by marine processes, estuarian tides and things like that. And that has reduced that reworking, rather than improving the permeability, has destroyed the permeability. So you go up in this part to a lower permeability interval, so we don't call it a flow unit. And then you've got a marine shale on top of that, which gives you that shaly log response. Okay, so what I'm going to do now is I'm going to skip back, show you a picture that I showed you before lunch. And it's this picture here, which is very important as a general model for these fluvial incise valley or point bar type reservoirs. And again, think of it in terms of the processes by which the sediment was deposited in that valley. So we had the formation of the valley during a drop in sea level, and then during early rise, you might get fluvial deposits at the base. But as you go higher in the stratigraphic section, sea level is rising, and so at some point, the marine waters spill into that valley, and you rework. You get estuarine deposits with a marine influence. And then above that, if sea level continues to rise, above that you get a nice marine shale. So that's exactly what you're looking at. I'm going to go forward now. And that's exactly what you're looking at. In this case, you go from fluvial channel sandstones at the base. Okay, the base of your fluvial channel is going to be right here. You have marine shale below it. You got a little shallow marine shale a little bit above that, but then you go into non-marine. So your first non-marine deposits in this incise valley are going to be your fluvial channel sands. And then as you move up stratigraphically, higher in the section, you get up into the reworked estuarian sands. And then with continued rise in sea level, you go up into the marine shale. So what you see here in this particular example is just like the cartoon I showed, which is a general model for the type of fill that you find in an incise valley. So what you're going to do then, in this case, you want to drill your well low. You want to perforate low in the reservoir where you're going to get your good high permeabilities. But there's one problem here, is that you have some low permeability shale streaks. You've got one right there, low permeability. You've got another one right here, and you've got another one right there. Low permeability streaks that are within the high permeability channel sands, fluvial channel sands. Those low permeability streaks can be mapped all the way around. They can be mapped all the way around the field. And what they really are is what we call caliche. They're, when you have a riverbed that is dry, you often get a calcareous or carbonate kind of soil on top of that dry riverbed. And that's what was the case here, to give you these low permeability streaks within the high permeable fluvial sands, fluvial channel sands. So periodically you had a drying up of your river, and you'd have the deposition of this caliche. And then the river would flow again and deposit channel sand, and then dry up again, and so on. Now, when you map these around the field, they turn out to be, in part, permeability barriers. They're thick enough and they're no permeability, so fluids can't get past them. So you've got another degree of compartmentalization. Not only do you have stratigraphic compartmentalization, where you go from a reworked estuarian sand of low permeability to a lower channel sand of high permeability, but you've also got these low permeability streaks in here. That's going to add a level of complexity to your reservoir. So what you're looking at here is a map of static pressures, static reservoir pressure, okay? And they're color-coded according to 4 different colors, and those 4 different colors represent 4 pressure trends. So here we have depth in a well on our vertical axis, and we have pressure in our horizontal axis. As you would expect with depth in a well, your pressure is going to increase. But what you see here, when you look at when you plot all the data points, you find that really there's 4 separate trends. Not one trend of increasing pressure with depth, but 4 separate trends. The red trend here, which is the highest pressure, if you look at the color coding, let's see, I'm going to color code this as it should be. Put some red in here. Okay, so here's the red trend, and if you look at where those wells are distributed, 3 of those wells are in this area here, and there's a 4th one, a red well, right there. And they form that trend of increasing pressure with depth in this particular area. So this was your higher pressure area. Now the green one, let's look at the green one. That's this trend here. Again, you get an increasing pressure with depth, but along a different trend line, meaning it's a different pressure compartment than before. And if we look at the distribution of the green wells, 3 of them are here. There's a couple here. I think that is 2. So I think they're basically around in this part of the field. So you've got another pressure compartment. So now we've got 2, a red one and a green one. Now let's look at this blue one. That's this trend right here. It's a separate trend, and if we look at the distribution of the blues, they occur kind of right in this area here, more or less. So we have a different pressure compartment over here. And then finally, if we look at the yellow trend, there's just a couple of data points for that one that they plot here, and if you look at the distribution of those wells that form that trend, they occur up in here. So you see you've got, by doing the pressure testing, you've got 4 different compartments that are outlined or defined by the variations in the pressure trends. Okay? If you had a single trend of pressure versus depth in these wells, then there'd be no compartmentalization. I think I said yesterday that for a geologist, the best information you can get is pressure data. If you're trying to figure out reservoir characterization and compartmentalization, the best data you can get is pressure data, because that pretty much tells you where you've got, if you've got connectivity of the sand bodies, and if you don't, it tells you where you've got the disconnects. Well, this was a company that owned this field, and they became very puzzled when they saw this. They wanted to do some infill drilling, but they looked at this pressure data and said, we don't really know where to put our next wells. In fact, they had drilled a few wells that weren't what they expected. So again, we've got these 3 different flow units with the pressure trends, okay? And where would you put your infill wells? Well, this is just the same picture again. Now in this field, they had 3D seismic, and that turned out to be very useful. And what you're looking at here now is 3D seismic. Here you see that meander bend there. So this is probably, the red is probably nice point bar deposits on the inside bend of a meander loop. And what you see is some different colors, reds and greens and little yellows, indicating heterogeneity, not necessarily compartmentalization, but certainly a reservoir that has heterogeneity with it, or variability. Well, when you put the well log data together with the well log and the core data together with the seismic, this was the picture that emerged of the reservoir. Very complex. Now here's basement down here. You had a limestone basement with a fault, and then limestone basement, another fault here, a little high, then a drop down there, and another drop down there. So that's basement. So really what you've got here is a Horst and Graben system. You've got a little Horst block up here, another Horst block over here, and then Graben system down in the middle. And so what you get, and another Graben down in here as well. So for that reason, you get a thicker fluvial deposit, Sites Valley fill, where you have the Grabens, the two Grabens, and where you have the Horst block, you didn't get any sediment deposited on that Horst block, and so that's not surprising. So there's a structural control here. Apparently the structure was there at the time of deposition of the sand, of the fluvial sands, and helped form that channel that was a meandering channel with a Horst block kind of in the middle of that. So the meander bend came around and came back up like that, something like that. Now when you look at the sand bodies, it's just kind of like the last exercise you did, where you've got isolated sand bodies. You've got channel sand 1, which occurs here on this side of the Horst block, and then on this side of the Horst block. Let me get rid of some of these colors here. Okay, so you've got channel 1 here. Channel 1 wrapped around the Horst block and came back on the other side in the Graben. So there it is again. So in 3 dimensions, this is probably a continuous sand body, but in 2 dimensions, it's not. Okay? Now, channel sequence 2, a separate sequence. Channel sequence 2 here, channel sequence 2 there, and the little checkered features here are those caliche deposits that are forming permeability barriers. So you've got a permeability barrier there and another one there around channel 2. But at the same thing, at the channel 2 wrapped around that Horst block, around both sides of it. So in the 3rd dimension, it's probably continuous, but in 2 dimensions, like the cross section, it isn't. Channel sequence 3, this one here, and it's the same story here. Comes around the side of the Horst block. And then channel sequence 4 is another one that just truncated through channel 3 and channel 2. So that adds another complexity. You've got some erosional surface here between channel 3 and channel 4. Then, to top off the sequence, you've got this reworked sand that tops off the sequence. So here you get oil wells. The black dots are oil wells in the sand body. As soon as you get outside or along the flanks of that sand body, you get a dry hole here and you get a dry hole over there because there's no sand there. So your valley now has been controlled by your structure by faulting. So the valley actually comes down like this, across like that, comes up, something, well, actually something like this. Okay? Now, when the operator of this field saw how complicated the geology was, first they said we were crazy. Okay? You geologists, again, making simple things very complex. And we said, no, we're pretty sure of it. But the operator didn't believe us. So, and still didn't want to drill any more infill wells. So we convinced the operator to do a seismic survey over a small area. And this was the results of the seismic survey across this interval, across the reservoir interval. So this is a survey. Now when you look down, you're looking down at the, this is a P-wave survey, 3D seismic survey, and you can make out kind of that bend in the channel. You can see that. And you also see some amplitude discontinuities. But it's still, it's kind of blurry and not very good, not very definitive. So we convinced the operator to also do an S-wave, shear wave seismic survey. What that allowed us to do is to take the amplitude data and convert that into velocity of the P wave over the velocity of the S wave down here. And when we did that, you get a very clear picture then of how highly compartmentalized this reservoir is. And you can see, if you look closely, you can see where wells were drilled. And what you find out is that there's actually some yellow areas that have never been drilled. The yellow is the sand in this case. The green is shaly and the blue is shaly. And there's some areas that have not been, where the yellow has not been drilled. And so those became the drilling targets. So it became quite simple once we showed the operator, this is what your reservoir looks like. That's the bad news, it's complicated, but the good news is you now can pinpoint where you want to put your infill wells because you did this combination P-wave, S-wave survey, shear wave survey. Well, why don't we take a break, okay? And I'll go and give you another example after the break.